Hello and namaste. Myself is Ramesh Bhandari. Today I am here to discuss on a topic of gram staining techniques. The gram staining it is a most widely used staining techniques in microbiology. It divides the whole the groups of bacteria into three main categories, that is a gram-positive bacteria, a gram-negative bacteria, and gram-variable bacteria. That is, a gram staining, it is a most commonly used staining techniques in medical microbiology, and it divides the whole the groups of bacteria into three main categories, that is a gram-positive bacteria, a gram-variable bacteria, and a gram-negative bacteria. Since it divides the whole the groups of bacteria into three broad categories, that is a gram-positive bacteria, gram-variable bacteria, and gram-negative bacteria, these types of staining techniques, it is also known as a differential staining techniques. Gram staining, it is one of the examples of a differential staining techniques. Why it is known as a differential staining techniques? Since the gram using the gram staining techniques, after the gram staining techniques, it categorizes the whole the groups of bacteria into three broad categories, that is a gram positive bacteria, a gram negative bacteria, and a gram variable bacteria. Since it divides the or it categorizes the whole the groups of bacteria into three main categories, it is known as a differential staining techniques. These staining techniques, it was first developed it was formulated by a Danish bacteriologist, Christian Grams. Since it was discovered or it was identified by or it was the staining techniques was formulated by the Christian Grams. So the staining techniques, it is known as a gram staining. So the in honor of the of a discovery of a Christian Gram, the staining techniques, it is known as a gram staining techniques. There are the certain there are the four reagents which are used in the gram staining techniques. That is a primary stain, which may be the crystal violet or the methyl violet or the Jensen violet. We can use either of one, either one of these. That is, we can use either the crystal violet or either the methyl violet or the Jensen violet can be used as a primary staining techniques. And another reagent, that is a mordants. We use a grams iodine. We use a grams iodine as a mordant in a gram staining. In another third chemicals, it is a decolorizing agents. That is, a different decolorizing agent can be used in a gram staining. You can use the acetone, or you can use a 95% absolute alcohols, or maybe you can use acetone alcohols. Maybe use either one of these can be used as a decolorizer agent in a gram staining techniques. And another is the fourth, the chemical reagents or the reagent in a gram staining. It is a counter stain. We can use the different types of dyes or the different types of stains as a counter stain. We can use either the safranin, or we can use a neutral rate, or we can use the dilute carbon fusion as a counter stain. Generally, if you see the gram positive bacteria, they appears in a purple colors, while that of a gram negative bacteria, they appears in a pink color. If you see here, the primary stains, the color of a primary stains, that is a crystal violet or the methyl violet or the Jensen violet, it is in the purple in color. While if you see the the color of a counter stains, that is a safranin or the neutral red or the dilute carbon fusion, their color it is a pink in colors. In a general, we can say the gram positive bacteria, they retains the color of a, in a general, we can say the gram positive bacteria, they retain the color of a primary staining, that is either the crystal violet or the methyl violet. They retain the color of a primary stain and appears as a purple in colors. while that of a gram-negative bacteria, they retain the color of a counter instance. They retain the color of a counter instance, that is a saffronin, and appears as a pink in color. And appears as a pink in color in a gram staining. Now, there are why the gram-positive bacteria they retain the color of a primary stains and appears as a purple color, while that of a gram-negative bacteria they retains the color of a counter stain and appears in a pink in colors. There are the several theories. There are the certain principles regarding why the gram-positive bacteria they appears in a purple color, or why the gram-negative bacteria they retains the color of a counter stain and appears in a pink in colors. There are the certain theories. Generally, there are the four theories. That is, the first theory is it is about the acidic protoplasma. Generally, if you see the bacteria inside the bacteria, inside the cell wall, there is a presence of a lipid bilayers. That is, then there is a presence of a nucleic acids. Generally, the nucleic acid it is generally acidic in the natures. The nucleic acid of a bacteria or the human beings, it is acidic in the natures. But if you see the acidic natures of a protoplasma of a gram-positive and the gram-negative. If you see the protoplasma of a, if you measure the pH of a protoplasma of a gram-positive bacteria, the protoplasma of a bacteria it is highly acidic. The pH might be around 2 to around 3. While that if you measure the pH of a gram-negative bacteria, it is less acidic as compared to that of a gram-positive bacteria. It is acidic, but as compared to that of a gram-positive bacteria, the pH of a gram-negative bacteria it is relatively low as compared to that of the protoplasma of a gram-positive bacteria. Now, what does this protoplasma will do? What will happen if there is a presence of a high protoplasma, high acidic protoplasma? Since we know that the crystal violet or the dye which is used as a primary stains or either the counter stains, either the crystal violet or either the methyl violet or the Jensen violet, these all the dyes are basic in the natures. They are basic in the natures. What will happen is, suppose this is a bacteria, this is a protoplasma of a bacteria. Now, if we add a basic dye, that is a crystal violet or the counter stain, what will happen? The base which is added on a bacteria, it moves toward the acid. It moves toward the acid, right? Now, depending upon the pH, what will happen? If the pH is high, then what will happen? More and more basic dyes should be the more and more basic dyes will move toward the acidic protoplasma to make it neutral, right? To make it neutralize, what will happen? More and more the basic dyes should be moved toward the acidic protoplasma. What will happen is we said that the protoplasma of a gram positive it is high. Then what will happen? More basic dyes will get entry into the protoplasma of a bacteria. But if you see the protoplasma of a gram-negative bacteria, what will happen? It is less acidic. It is less acidic as compared to that of a gram-positive. Then what will happen? There is a movement of a basic dyes in a protoplasma of a gram-negative, but the movement, the concentration of a dyes or the quantity of a dyes which has moved from the outer surface of a bacteria to the inner surface of a protoplasma of a gram-negative bacteria, it is relatively less as compared to that of a gram-positive bacteria. What will happen? The protoplasma of a gram-positive bacteria, it is more. It holds it accumulates the more basic dyes, but the protoplasma of a gram-negative bacteria, it holds the less basic dyes as compared to that of a gram-positive bacteria. Now we'll discuss it later on. Now, in another theory, it is a lipid cell wall theory or the cell wall content theory. It is the most widely accepted theory. We'll discuss it in the later part one. And another is a cell permeability theory. As you know that the gram-positive bacteria cell wall, it is made up of lipids, while that of a as you know that the gram-negative bacteria cell wall, it is made up of lipid bilayers, while the gram-positive bacteria cell wall, it is made up of peptidoglycans. Now, the lipids are more permeable as compared to that of a proteins or the carbohydrate. What will happen? Due to the permeability of a cell wall of a gram-positive bacteria, the stain which has get entry inside due to the high permeability of a bacterial cell wall, due to the presence of lipid content, that is the lipid content in a gram-negative bacteria, it is relatively high as compared to that of a gram-positive bacteria cell wall. Now suppose the dye which has been added, which the basic dye, that is the crystal violet, which is added over the bacterial surface. What will happen? They will die. It will get entry into the bacterial protoplasma. Now, when you add a decolorizing agent, what will happen? The decolorizing agent, that is either the acetones or either the acetone alcohols or the 95% ethyl alcohols, what will happen? It will dissolve the lipid content of a bacterial cell wall. What will happen? Now the bacteria, it loses the outer cell wall. What will happen? There is complete. Now the bacteria will loses the outer cell wall. What will happen? The dyes which has reached to the bacterial protoplasma in a primary staining techniques in the first state. Now they will come out. Now, if all the dyes that comes out, what will happen? The bacteria become a colorless now. The bacteria become a colorless. See, but in case of what will happen? In case of gram-positive bacterial cell wall, it is made up of peptidoglycans. What will happen when you add a decolorizer? What will happen? The bacterial cell wall will shrink. Suppose it was the original shape of a bacteria. Now what will happen if the bacteria shrinks? Shrinks means the size become relatively small. What will happen? The cell which was present, now the bacteria will become compact. When the bacteria become compact, what will happen? The permeability of a cell wall, what will happen? It will decrease. Now the acetone or the decolorizer agent which has been added to the bacterial cell wall cannot reach to the bacterial protoplasma, so that the dye, and it cannot break the diiodine complex. If they cannot break the diiodine complex, what will happen? The dye cannot comes out. The dyes which has entered to the bacteria cannot comes out. Now, thus the bacteria retains the color of a primary stains. We'll discuss it later on in a brief, in a details. Now another theory is a magnesium ribonucleotide theory. They believe that the magnesium ribonucleotide, it is only present in a gram-positive bacteria, but it is absent in a gram-negative bacteria. It is only present in a gram-positive bacteria. What does this magnesium ribonucleotide will do? It will combine with the diiodine complex. It will combine with the diiodine complex and hold the and make it water insoluble and make it insoluble to the water. But it is lacking on a magnesium ribonucleotide. It is lacking on a gram-negative bacteria, so that they cannot form a magnesium ribonucleotide diiodine complex. As a result, what will happen? The dye, during the time of washing of a bacterial smears, in every steps, what will happen? We used to wash in the tap water or with the distilled water, right? Then during the time of washing, what will happen? The dyes will goes out. Now, before moving to the cell wall theory, we'll discuss the cell wall theory in the details. Let's see the structures of a gram-positive bacterial cell wall and the gram-negative bacterial cell wall. See here, this layer, 1 layer, 2 layer, and 3 layers. It is a cell wall, this cell wall of a gram-positive bacteria. It is made up of a peptidoglycans. See here, there is a 3 layers of a peptidoglycans. Generally, the cell wall of a gram-positive bacteria, it is made up of 3 to 4 layers of a peptidoglycans. There are 1 layer, 2 layer, and 3 layers of a peptidoglycans. Well, that and a small layers of the small layers of lipids, that is a cytoplasmic, that is a plasma membrane. But here, if you see in a gram-negative bacteria, see here, there is 1 layers of lipids, lipid membrane, the outer layer. The inner, this is the outer layer, this is the inner layers. In between the outer layer and the inner layer, there is a presence of a 1 layer of a single thin layer of a peptidoglycan. It is present. A thin layer of a peptidoglycan, it is present here. Now here, see here, relatively, the layer of a peptidoglycan is very thin as compared to that of a gram-positive. But the layer of a lipid bilayers, outer lipid membranes, it is very more, it is high in a gram-negative bacteria. Did you see here in the gram-positive bacteria? There is no lipid layer. But in case of a gram-negative bacteria, that is their cell wall, it is made up of a lipid content and a thin layer of a peptidoglycans. There is a space in between the outer membrane, that is a lipid membrane, and an inner cytoplasmic membrane, that is a plasma membrane. There is a space is present. This gap, it is known as a periplasmic area. The periplasmic area. Now here, the difference in a gram-positive bacterial cell wall and gram-negative bacterial cell wall is the gram-positive bacterial cell wall, the majority of cell wall, it is made up of a thick layer of a peptidoglycans. While in case of a gram-negative bacteria, their cell wall, it is made up of thick layer of lipids and thin layers of peptidoglycans. Now see here, this is the same. Here, this is a peptidoglycan layer, and this is a plasma membrane. Here, this is a lipid membrane. The lipid, this is a gram-positive bacterial cell wall. This is a gram-negative bacterial cell wall. Here, this is a lipid membrane. That is a lipid membrane. This is a protoplasmic membrane. That it is a peptidoglycan layer or thin layer of a peptidoglycan. This is a plasma membrane. This is about the structures of a gram-positive bacterial cell wall and gram-negative. That is a gram-negative bacterial cell wall and gram-positive bacterial cell wall. It is a thick layer of a peptidoglycans, right? Now we'll see here. As I mentioned there, in the gram staining, the primary steps, it is a primary staining. In a primary staining, we use a crystal violet, or the Jensen violet, right? When we add, we'll move to the, this is a lipid, this is a cell wall theory, or the lipid content theory, is cell wall theory of gram staining. Now see here, when you add a primary staining, that is a primary staining, it is a crystal violet or the Jensen violet on a bacteria, on a surface, on the outer cell wall of a bacteria. What will happen? Due to the, as you mentioned, that the protoplasma, that is the cytoplasma of a bacteria, it is acidic in the nature. It is acidic in the nature. So what will happen? The dye, it is a basic, it is a base. What will happen? The base will move towards the acid. The base will move towards the acid. What will happen? The primary stain which is added on a surface of a bacteria, they moves inside the protoplasma of a bacteria. Now the bacteria, it moves from the outer surface to the inner surface, inner protoplasma surface of a bacteria. Here, in case of gram positive, in case of gram negative also. Here, see here, this is a gram negative bacterial cell wall. The primary strains, which will move from the lipid bilayers, then the thin layer of a peptidoglycan, and reach to the protoplasma of a bacteria. And as I mentioned earlier also, the protoplasma of a gram positive bacteria, it is highly acidic, right? 2 to around 4 pH. As compared to that of a gram negative bacteria cell wall, a gram negative bacteria protoplasma, which is less acidic, that is around the 4 to around 6, right? 4 to around 6 pH. Now see here, as I mentioned you that if the protoplasma is high, it is more acidic, then what will happen? More and more basic dyes will get into the protoplasma of a bacteria to neutralize the acidic content, to neutralize the acidic. The acidic natures of a nucleic acid of a bacteria. Here, the more and more dyes has entered to the protoplasma of a bacteria. More dyes has entered to the protoplasma of a bacteria. But in case of a gram negative bacteria, it is less acidic as compared to the relatively less acidic as compared to that of a gram positive bacteria. Now, what will happen is there is a movement of a dyes, that is a primary strains to the protoplasma of a bacteria. But the quantity of dyes or the stain which has entered into the protoplasma of a bacteria, it is relatively less compared to that of a gram positive bacteria. Why this happens? It is due to the less acidic natures of a protoplasma of a gram negative bacteria. Till here, it is clear in both the gram positive bacteria and the gram negative bacteria, the crystal violet will reach to the protoplasma of a bacteria and stain the bacteria as a purple in colors, and stain the bacteria. Both in the primary staining techniques, in the first steps, both the bacteria will take the color of a primary stains and appears in the purple in colors. Same here, it is repeated here. Now, in the second steps, it is a mordant. We'll add a gram iodine as a mordant, right? In a gram staining, this is iodine, that is a brown color, that is brown color iodines. What will happen is this iodine will add the iodine on both the bacterial cell wall, on both the bacterial smears. What will happen is this iodine get entry inside the bacterial protoplasma. That get entry inside the bacterial protoplasma. See here, this iodine is also the basic in natures. It is also basic in the natures. Iodine also basic, but the protoplasma of a bacteria, it is acidic, it's still acidic. The dyes which has been entered, the basic dyes which has been entered inside the bacteria, it is not enough to completely neutralize the protoplasma of a bacterium. Now there is a movement of a dyes, that is there is a movement of a moderate, that is grams iodines inside the protoplasma of a bacteria. Yes, here same here in the gram negative bacteria. It is gram negative bacteria. The gram, that is a grams iodine, it will get entry into the protoplasma of a bacteria. Now what does the grams iodine will do? The first thing is a grams iodine, it will combine with the dye. That is, this is a dye, this is a crystal violet. It will combine with the crystal violet, that is iodine. Crystal violet and iodine, grams iodine, they combine and form a crystal violet iodine complex, which is known as a diiodine complex. Now they will form a diiodine complex. What will happen is, if there is a formation of a diiodine complex inside the protoplasma of a bacteria, suppose the size of a dye, it is 1 micrometers. Similarly, the size of a grams iodine, it is also 1 micrometers. Now if they combine together, what will happen? 1 plus 1, it will become a 2 micrometers, right? Which one is small? Either 1 micrometer is small or the 2 micrometers. 1 micrometer is small, 2 micrometer is big, right? The size become a, what will happen? The size become a large. Now see here, suppose the bacterial cell wall, which is having a bacterial cell wall, it is possess pores which can allow the entry of a dyes or the chemical which size is 1 micrometers in the diameters. Because earlier the dye, it is also having a 1 micrometers diameter, so that it can measure the size of a dye is 1 micrometers. Let assumes, right? Okay, the size of a dye, it was 1 microliter, so that it get easily get entry into the protoplasma, because the pore size which allows the entry of a bacteria of a dyes to get entry, it is 1 micrometer size, then can it get easily entry. Similarly, the size of a grams iodine is also, suppose it is small 1 micrometers. What will happen? It also get easily entered. But as it reaches to the protoplasma of a bacteria, the size, they combine together and form a diiodine complex. Now the size become a 2 micrometers. Now can you assume that? Can you say that a 2 micrometer size object can comes out from a 1 micrometers rod, the 1 micrometer pore? It is impossible, because this, since the size of a diiodine complex is relatively high, now this object, it cannot be comes out from the outside outside the bacterial cell wall, because the size of a path which is present on a bacterial cell wall, it can allow only to comes those objects which has a size of 1 micrometers. But The iodine, what it does, it combined with the dye that is a crystal violet and from a diiodine complex. Now the size of a is 2 microliters. It is relatively big as compared to that of a earlier size. Now these dyes cannot comes outside the bacterial cell. Now the dye, it is fixed now. It cannot be comes out, right? Here till now, here it's okay. It's from a now. Now the third steps, we'll move through the third steps. In a second step also, the bacteria will retain the color of a purple color, will retain the color of a primary stain and appears in the purple in colors, right? Now, in the third steps, it is a decolorization steps. Decolorization steps. We use acetone or the acetone alcohols or the ethyl alcohols, right? We use 95% ethyl alcohols. Now, as you add acetones over the bacterial smears, what will happen? In case of a gram-positive bacteria, it will causes the shrinkage of a cell. It will causes the shrinkage of a cell. Did you notice here? Just see here the size, and let's see the size here. Did you see here the shrinkage? Earlier the size of the thickness of a bacteria was more. Now, if you see the thickness, what will happen? The thickness has decreased. It is why it happens. It causes a shrinkage. Of a bacterial cell wall in case of a gram-positive bacteria. The acetone, it will do the decolorizing agents which is added on a bacteria. It causes a shrinkage of a bacteria cell wall. And did you notice here the path? See here this area. It is almost close here. If you see the earlier, see here the gap. There was a gap, right? But due to the shrinkage, what will happen? The gap which is formed between the different molecules of a peptidoglycans, they comes very close and close. What will happen is the path is almost blocked. Now, the decolorizing agents, the main objective of adding the decolorizant, what is? To remove the color, right? Decolorizers, to remove the color which has get entry into the endoplasm of a bacteria. But due to the shrinkage of a bacterial cell wall, in case of a gram-positive bacteria, the acetone cannot reach to the protoplasm of a bacteria. If it cannot reach to the protoplasm of a bacteria, then it cannot dissociate the diiodine complex into the crystal violet and iodine. It cannot decompose, or it cannot break the diiodine complex or to the crystal violet and the iodine complex. The dyes cannot comes out the cell wall of a gram-positive bacteria. Cannot comes outside the cell of a gram-positive bacteria. But in case of gram-negative bacteria, what will happen? See here, see the arrow, okay? Just look at the arrow. The arrow it is upside. The arrow it is upside here. Now, when you add acetones, when you add acetone or the ethyl alcohols or the 95% ethyl alcohols or the acetone alcohols on a bacteria, on a bacterial smears, what will happen? Did you notice here? Did you notice here? This is the outer cell wall. It is made of a lipid bilayer. Did you see here? There is no presence of a outer membrane, that is a lipid bilayers, the lipid layer. What will happen is here, when you add acetones or the ethyl alcohols over the bacterial surface, what will happen? It will dissolve the lipid layers. It will completely dissolve the lipid layer of a bacteria. Due to the complete dissociation or the dissolving of a lipid layer of a gram-negative bacteria, what will happen? The bacteria will lose the outer layer, completely lose the outer layer, that is lipid layers. And see here, the area between the peptidoglycans layers, between the peptidoglycan molecules, between the intermolecules of a peptidoglycans, what will happen? There is a huge space. There is a huge space. Now, these acetones or the ethyl alcohols, it get entry into the protoplasm of a bacteria, get entry into the protoplasm of a bacteria. Now, here the acetone or the acetone or the decreasing agents, it get entry into the protoplasm of a bacteria. What will happen? The dye, it will dissociate the diiodine complex into the crystal violet and iodines. Now, earlier their size was how much? 2 micrometers. Because of their size 2 micrometers, they cannot come out. Now, when they dissociate, what will happen? The size become each molecules become 1 micrometers, because a single 1 micrometer size, earlier the size that the diiodine complex size was 2 microliters. When they dissociated into the crystal violet, the size is 1 microliters. The iodine crystal grams iodine size is 1 micrometers. Then what will happen? The size become a small. Now, if the size becomes small, what will happen? Now the dyes will comes out. Now the dyes will comes out the cell wall, through the cell wall. This is because of two factors that place, that is due to the complete dissolving of our lipid bilayers due to the decreasing agent, that is a acetone or the 95% ethyl alcohols or the acetone alcohols, it completely dissolves the outer layer of a gram-negative bacterial cell wall, that is a lipid bilayers, and get entry into the cytoplasm of a bacteria, and when it reaches to the cytoplasm of a bacteria, it dissociates the diiodine complex and form a distinct molecules, that is a crystal violet and the iodine. Now the crystal violet and iodines, they comes out the bacterial cell wall. Now the bacteria will become a colorless. See here, all the dyes and iodine which has reached to the endoplasm of a bacteria, there is no any dye, there is no any crystal violet or the trans iodine into the protoplasm of a bacteria. All they comes out and bacteria become a colorless. But in case of a gram-positive bacteria, as we add acetones, due to this, it will cause a shrinkage. As the cell, the peptidoglycan layer shrinkage, what will happen? The path through which the acetone will reach to the protoplasm of bacteria, it is blocked. As it is blocked, the acetones cannot reach to the endoplasm of a bacteria. As it cannot reach to the endoplasm of a bacteria, it cannot break the diiodine complex. As the diiodine complex cannot be broke out, the dye cannot be comes out. the cell wall of a bacteria. So the bacteria will retains the color of a primary stain and appears as a purple color. But in case of a gram-negative bacteria, due to the complete movement of a bacteria due to the complete dissolving of a cell wall of a bacteria, the acetone break the iodine complex. As a result, what will happen? Both the dyes in iodines will comes out and bacteria become a colorless. Now the final steps, it is a counter staining. That is, we use a safranin or the neutral red is a counter stain. In a counter stain, the color of a counter stain is a pink in colors. It is a pink in color. As you see here, is the color, it is pink in colors. As you see here, the pink, it is a gram-negative bacterial cell wall. It is pink in color. What will happen here, as you add the safranin over the cell of a gram-positive and the gram-negative, a few molecules of a counter stain will get entry into the protoplasm of a gram-positive bacteria. But in case of a gram-negative bacteria, hold the here. This is a first step. That is this second step. Now, in case of a gram-negative bacteria, as we add a safranin, that is a counter stains, all the counter stains, that is a safranin, get entry into the protoplasm of a bacteria and stain the pink in colors. But in case of a gram-negative bacteria, in case of a gram-positive bacteria, only the few molecules of a crystal of a counter stain, that is safranin, get entry into the protoplasm of a gram-positive bacteria. But the effect of this stain, it cannot completely change the color of a primary stain, that is a crystal violet, so that the bacteria will appear as the purple in colors. But in case of a gram-negative bacteria, since it has lose the primary stain during the decolorizing steps and appears as a colorless, as we add a counter stains, it will take all the counter stains and appears in the pink in colors. So that we can say the gram-positive bacteria, they will retain the color of a primary stains, that is a crystal violet, and appears in the purple in colors. While that of a gram-negative bacteria, they retain the color of a counter stains, that is a counter stain, that is safranin, and appears in the pink in colors. They appears in a pink in colors. It is about the cell wall theory or the lipid content theory of a gram staining. So here, it is a one schematic diagrammatic representation of a gram staining. Both in the before the staining, all the bacteria, both the bacteria are colorless. As we add a crystal violet, both the bacteria will take a crystal violet. That is iodine, they will appear as a purple. But as we add the decolorization, what will happen? The gram-negative bacteria will lose the primary stains and become a colorless. While the gram-positive bacteria, they do not lose the colors and appears in the purple in colors. As we add a counter stains, the gram-positive bacteria, they will retain only a very little amount of a safranin, while that of a gram-negative bacteria, they retain a very large quantity of safranin and appears as a pink in color, while the gram-positive bacteria retains a very few molecules of a safranin that is not enough to change the color of a primary stains and appears in the purple in the colors. Here, the color, this is a figure, a deep violet deep purple color bacteria, it is a gram-positive bacteria. A pink color bacteria, it is a gram-negative bacteria. What is the significance of a gram staining? It is fast and inexpensive methods and may suggest and helps in early identification of a pathogens and helps in the treatment of a patient. What is the limitation of a gram staining? The staining techniques, that is the every steps of a gram staining, it is very, very sensitive. Particularly the decolorization steps, it is very important. It is very sensitive. You should be very careful in a decolorization steps. If you do the decolorization steps for the long time, then what will happen? The gram-positive bacteria may appear as a gram-negative bacteria. If we do the decolorization steps for the very short period of the time, what will happen? The gram-negative bacteria will appear as a gram-positive bacteria. So that the decolorization steps, it is a very crucial, it is a very important steps in a gram staining. Thank you. That is about the gram staining. I hope this lectures, it will be very helpful in understanding the mechanisms of our gram staining. Thank you all.